Here's a real use of the rotation matrix. So it's space mechanics, and obviously I got the images from NASA, then modified it like crazy. So yes, these images, this Earth images from NASA. So what I'm doing is AJ is a movement from one coordinate transformation to another. Now, this is like one of the first times that you will ever see, what's the right terminology to say it? A change in coordinate that makes sense. Because a lot of times what you will see later on is in dynamics is different than you ever could have imagined. You'll see that the coordinate changes with data and it's active changing, where you go and see it as time changes, the coordinate changes and it's confusing. This, on the other hand, is actually more digestible and understandable. So what is this? We have this over here. Now this points to a constellation, or it used to. Now I think they changed the notation because the constellation moves around. The Orion Horn, I believe is, I forgot what it's called. But basically used to do that. Now it doesn't. But you can get the general idea. What the idea is that you can easily get this format over here. This format will allow you to make this a 2D problem. 2D problems are much easier than dealing with 3D. And this is what you get ultimately. And this is what you want. You want a, a easy 2D, solutions are easy. But in reality, you need to understand that the if there's other orbits and then you want to interaction of these two, you want to go back to IJK. Okay? So the easiest way to figure out the connection between two is go this way because going backwards is easier than cakes fly. You'll see what I mean. So, all right. Now I'm going to say again. Here's the use of coordinate rotation transformation and how it works. The first thing you need to know is IJK. IJK is over here. And then there's PW. I think I called it that. And you see a change rotation in the Z direction, which is done by this over here, as you can see. Oh, I should change that to Z. I made a typo over here. Very common mistake. I could just change it real quick. So over here is supposed to say Z, and this is supposed to, yeah. Okay, we're good. We're good. All right, let's continue here. Um, I think you understand what these are. These are coordinate translation. Imagine this being coordinate, and you're changing this and doing that basically is what's happening. So again, this is the x-axis rotation, this is the y-axis rotation, this is the z-axis rotation. We now understand that. I should have led with that. That's my mistake. I didn't think about that. I just went full blown to this question because this question is one of the more intuitive ones, in my opinion. Anyway, we're going from actually a lot of times you go from this coordination back to IJK, but for the sake of argument, what we're gonna do is basically we're gonna go from IJK to QPW. The reason why we're doing that is because it makes it easier to go back to that one. You'll see why. Okay? Now, we'll start off with IJK and a rotation in the Z direction. Z direction allows you to get this big omega, which will change it to a new temporary frame. This frame, then you rotate on the X direction over here, which will move over here. And finally, you'll again, with this temporary kind of frame, you move again in the Z direction for that thing. So you basically rotate this multiple times to get it to the QPW to make life easier to calculate, certain things. Anyways, that matrix is formed, And as you can see over here, this is the formal way you can see it. And I'm gonna make probably one question on this because this is like really hard. Anyways, as I said, I should probably go up over here first. Going to PQW to ECI, ECI is IJK. It's just doing this step over here. So starting with this over here and applying the next matrix and then applying it again. Now those matrix make you get this big matrix over here. And you'll see something comically weird. The transpose the same as that, and that's because of how this is symmetric base is like and I believe it's like something like this. You can flip it. The matrix shows you if you transpose it, you get the inverse, and you can prove that out. It's something called well actually I don't really know. I used to know this. Huh. Well, it's an inverse matrix is what I'm trying to say, but I used to know how to prove it. I should probably relearn how to prove that. But anyways, that's what I want to say. So this is possible. Anyway, I finally went to rotational matrix, and now we're going to Volscian. And the Volscian is important for variation parts. I don't really, and then we're going to finally Laplace and Fourier transformation. Now we're going to do both of them because a lot of times we talk about one of them, but we don't talk about the other one. I want both of them in my textbook. Not I'm not gonna put it later on in the controls. We're gonna learn it here. Uh, that's the plan. Anyways, I'm gonna stop recording now. I think we can